To the main stage. We're going to have Kenneth Harris II to come up. And he's known for delivering thoughtful, dynamic leadership on programs of critical national and international importance. I mean, he started his journey in NASA at 16 as an intern, and now, he got to work things that are actually in space. And he's going to come on stage. Kenneth, can you please join us and just tell a little bit about your journey and your story. A round of applause, please.
Appreciate you. Thanks, man. This podium is so far away from that side of the stage. How are you doing this morning? Good morning, everyone. So before I get started, if my slides would show, please, up there for me. Sorry, technical difficulties. Going to get the slides up there. All right. And play. Okay, there we go. All right, so here we go. In 1800, a German-British astronomer helped to open the door for all of us to, quite literally, change the way that we saw the universe. And like so many other great discoveries, he wasn't looking for what he found. He kind of stumbled upon it, right? Like so many other discoveries that we find across the human history. The astronomer by the name of Sir William Herschel was experimenting with prisms to understand, well, he had this habit of studying the stars and planets. He actually discovered Uranus. And he wanted to be able to observe the sun through his telescope with his naked eye. Right? And so he was going through the process of developing these filters so that it could lessen the sun's glare and lessen the sun's effect on the human eye. And so still to present day, no matter what president does it, I can make that joke because I'm American, no matter what president looks directly into the sun, it's not okay to look up at the sun to present day. And so, but what he discovered is through experimentation, simply put, is that if he placed his thermometer at the very end of the visible light spectrum near the red end, it was still heating up, basically, right? And what this showed him was that there was an invisible set of wavelengths that you couldn't see with your naked eye that still impacted upon that thermometer. That light was coined as dark heat. And we knew that as dark heat throughout all of the 1800s until close to the end of 1800s, early 1900s, when it was redefined as infrared light, which we know to present day. And so why do I bring up William Herschel? Why do I bring up that story at all? Well, again, he helped to set the building blocks for future inventions that helped us to redefine the space industry as a whole, and I'll get into that in a bit. And one of the most crucial inventions came apart in the 1920s, 1929 specifically by a Hungarian physicist. I don't get to tell that story a lot because this is my first time in Budapest and it doesn't really resonate anywhere else. But this Hungarian physicist by the name of Kálmán invented what we know today as the first infrared camera. And so this infrared camera gave military the ability to use basically night vision, right? And this is different than what we know as infrared technology today. This technology during that time was actually invented for military purposes. And why not? Because everything was created for military purposes at some point and then came over to science. And so this was classified as top secret information. It was then declassified in the 1950s because of studies from near infrared, mid infrared, and far infrared technologies. And so the question here that we have is, what has this discovery and ultimately the invention of this near-infrared camera done for us within the space industry? So primarily, it's opened our eyes to see the universe in its purest form. So what's behind me is it doesn't necessarily look like a totally black screen. On my slides it does. This looks a bit different, but you all can see that there's some kind of image trying to be shown here. And you see kind of those bright dots around. This is an example of what it would look like if you were looking into deep space with your naked eye or with a relatively mid-range power telescope. Is that working? And so that's what it looks like with the assistance of infrared. And I'll go back quickly. So you see these kind of brighter 3 series of dots there. You can see that if you look at it through infrared, this is again the universe in its purest form. And why? Because of a concept called cosmological redshift, and I'll get into that momentarily. But this is known as the pillars of creation. The pillars themselves, which astronomers often refer to as elephant trunks, are basically little stellar nurseries where star systems are being born. And at the same time, a group of massive stars are also dying. To put this in perspective for you, and some of you might recognize it better from this shot here. This is the 1995 Hubble image. This is the 2022-2023 JWST image. And so what we know from this image of this pillar here is the pillar on the left is a little over, so the pillar down near the bottom is a little over 4 light years in size. And 4 light years translate to roughly 40 trillion kilometers. So one light year is approximately 10 trillion kilometers. It's actually 9.461, something like that. But each of these, to put in perspective for you, the tip of one of these pillars can actually hold our entire solar system, just to put in concept for you of how small we are in the overall universe. And so these newly formed star systems and images come from an instrumentation on board the James Webb Space Telescope known as the Near Infrared Camera, or NIRI for short. And the last thing about this image, these bright reddish orbs down here, or spikes that look like they're kind of coming out of the dust cloud, are actually galaxies collapsing on themselves. And so throughout this presentation, I've kind of weaved in pictures like this because throughout the space industry, it's tough to be able to visualize what you want to see or be able to visualize what your concepts are. So a lot of oohs and ahs. So when I say ooh, you say ah. Ooh, ooh, ooh. Okay, that's a little better. And so before we go much, much further here, I want to take a minute to step back. So, and get this out the way up front. So I am not a software engineer. I'm a mechanical engineer by trade that has dabbled in rocket science and that currently works as an aerospace engineer helping to do cybersecurity for a lot of our satellites. The satellite that is nearest and dearest to my heart is known as the James Webb Space Telescope. I'm happy to be able to join you, honored to be able to join you today to talk about the blend between how our crazy scientists, our mechanical engineers, and our software engineers all come together to develop these programs that ultimately help us to see these pretty pictures, right? But they're not just pretty pictures, they also help us to understand where the universe came from and the direction that we are going as we continue to explore the vast cosmos. And so this image here is a picture of the James Webb Space Telescope. Does anyone know about the James Webb Space Telescope? Show of hands. Great. Has anyone worked on it? Yes, no one's worked on it, yes. So I can say anything I want up, no. So the James Webb Space Telescope is arguably the world's most powerful and most complex space system telescope. Does anyone know, show of hands, how many single points of failure the James Webb Space Telescope has? Show of hands for over 10. Over 20. Under 10. Okay, there are 344 single points of failure on this thing because we are mad men and women. And so let me just walk you through these images really quick. So your OTE, your optical telescope element, is going to be right there, those big gold-plated mirrors that everyone loves. They're actually not gold, they're gold-plated, they're actually made of beryllium. There's actually about the size of a golf ball in terms of gold actually on this thing. And when it's completely folded out, it's about the size of a tennis court. Over here to my right, my left, your right, is going to be Brian. Brian is taking the lens cap off of our James Webb Space Telescope before one of our testing phases there in his full bunny suit. This one's really important here. This is a stowed image of just the top portion of the James Webb Space Telescope. So the James Webb Space Telescope is divided into 2 sections, and I'll get into that in my next slide. This is known as the operational side, or the science-facing operational side, and that is the stowed configuration minus the sun shields at the bottom. So it's not nearly as wide as it is, but this is one step of how we fold it before we put it into the launch vehicle to actually get it into its L2 orbit. Then lastly, this image here, this is an image of OTE and ISOM. So combined, they're known as Otis because we love acronyms at NASA. And so Otis is a combination of the scientific instruments and the mirrors primarily to form that that scientific element of the James Webb Space Telescope. And this image is us loading it into Chamber A, which is where we tested a bunch of our Apollo missions down in Texas, about 10 days before Hurricane Harvey hit Texas. So we were absolutely nervous putting that thing in there. And I'm one of those people down there in the bunny suit. I'm on that side there, one of the shorter ones, but you can't tell. All right, so moving into what these two sides are and the science behind it. So on one side, you have the observing side, and on the other side, you have the sun-facing side. So for today, we just know them as the top and bottom of the satellite because we're creative sometimes, but other times we're very direct. And another name it has is the hot side and the cold side. So the hot side is going to be your sun-facing side. It's hot because it faces the sun, right? Observing side, it's cold because it faces away from the sun. And so for today, my audience, unbiasedly, is cold side because I worked on the cold side. I worked to build the cold side, the ISIM element, which is on the back of the OTE. So let me hear you say cold side. Cold side. There we go. So cold side. So the top portion of this, or let's start at the bottom, actually. The lower part of Webb is layered in these 5 layers of sun shields that face the sun, and it's where our equipment is shielded from the sun. But on the bottom, you have things such as your solar panels for obvious reasons, your communications, your GPS, your navigation, and your comms that send it back down to Earth, as well as a series of your star trackers where it gets into that software element, right? And I'll talk about that in a bit. And then the top part, the cold side, is where you find your primary mirrors, your secondary mirrors. So your primary mirrors, those 18 golden mirrors that you see up there, and your secondary mirror is on that boom, that black boom that you see extending from the front there. It's very important for the observing facing side to stay very, very cold because you need it to be looking into the darkness, the blackness of space. And so that 5-layer sun shield allows us to keep it at that temperature as it continues to passively cool. So just to show the difference between the two sides, the hot side is around 125 degrees C. I think I said that right because I'm trying to convert from F. 125 degrees C. And on the cold side is negative 235 degrees C. So it's about a 16-meter difference between these two sides and those 5 layers of sun shields. And it has to be that cold in order for it to actually see things in infrared light because that is thermal imaging. It's not thermal, but it's thermal imaging. Remember, we're biasedly cold side here. Biasedly cold side. Did it switch? Okay, so the phenomenon that we are observing with the James Webb Space Telescope is known as the concept is known as cosmological redshift. I'm just giving you some fun talking points for dinner parties, right? So cosmological redshift, it basically means that as the universe is constantly expanding, and we know the universe is expanding, the wavelengths are getting redder and redder. And the redder they get, the harder it is for your naked eye to see them. And so galaxies and star systems that are billions and millions of miles away don't necessarily make it to your eye here on Earth because of a number of things. One, we know the universe is extremely dusty. It's not just empty space, it's extremely dusty because things are blowing up, things are blowing apart, galaxies are swirling and imploding on themselves. And so it's full of dust from those leftover star systems. And not to mention that Earth has a number of atmospheres that you need to be able to see through in order to really see any of these things. So infrared light is able to pierce through dust clouds, it's able to pierce through anything that you might find in the universe, which is easier for our instrumentation to pick up, which is another reason why we launched this satellite, or James Webb, over 2 million miles away, or 1.5 million kilometers away, to an L2 orbit, and that L2 orbit faces away from, again, the sun, the earth, the moon, anything that could obstruct its view there. And so we know for a fact that the universe is made up of galaxies comprised of hundreds and thousands of planets and other celestial bodies. And so do something with me real quick for those who want to participate. Put your arm out like this for me, straight up. And put your index finger out. On the very tip of your index finger, imagine that there's a tiny grain of sand, all right? In that tiny grain of sand is basically what this image is when you look at it from the perspective of the entire universe, if this thing plays. Now we're all just standing with our hands in the air. You can lower your arm. And so On the tip of your finger would be just that starting image when you look at the entire galaxy as a whole. And this is not by any means just this entire galaxy. And so just to put in perspective for you, that each of these larger dots are potentially galaxies or star clusters that are made up of hundreds of thousands of millions of stars and planets and anything else out there, right? And so when you put that into perspective of what we are actually looking at, it blows my mind. I don't know if it blows your mind, but it blows my mind. And so this image, many might know it as the deep field image. This is actually James Webb's deep field image. And it's the same spot in the sky that Hubble looked at in the 1900s when they were exploring deep space star concepts, for lack of a better term. And so this is the enhanced version of that allows us, again, to really put in perspective how small we are in the overall universe. And this galaxy cluster is known as, remember the name, is SMAX 0376, which I'm trying to figure out who names these things so that I can get in the rhythm of it. Maybe I can name one too. But this is known as SMAX 0366. So if my slide will go to the next slide here. No? Okay. So as I mentioned, by specializing in infrared light, Webb will be able to see what's beyond the dust, and it has been able to see what is beyond dust. And moving from across the screen here, you start with visible light, which from ESO, which is a European Space Observatory, which is ground-based. It's a ground-based observatory that is looking at the same particular spot in the sky as Hubble did. But does anyone know what this nebula is called by any chance? Is anyone a space fan? Anyone know what this nebula is called by any chance? Okay, this is known as the Cat's Paw Nebula. Again, I don't name them. It's called the Cat's Paw Nebula. And it was captured by the European Southern Observatory in visible light near the right. And then moving toward the middle, you get your near infrared light. And then all the way at the end there, you see your mid infrared light. And that goes from ESO, which is, again, a ground-based, all the way to Spitzer, which, as we know, is one that actually orbit. So what does each type of light show you? In the visible light area, you see that stars are forming inside these dense clouds of dust, which scatter and then effectively block their visible light from reaching the telescope or reaching your ground-based observatory because of the atmosphere that is involved in it. In the near-infrared light, you can see that much more light is shining through these denser dust clouds that you see that are identified as red there, and even some of the darker black spaces and the lighter blues that you see there. So that's an example of near infrared or infrared light shining through these dust clouds and the very compact and complex nature of space. And then mid-infrared shows gas and dust clouds with heat from what we know or what we identify as some of our brighter, younger stars. So as stars are forming, they heat up before they form. And so within that, you can see in the mid-infrared light. And so what Webb's images are going to show, because none of these are Webb's images, but what Webb's images have showed is that you can see past the dust cloud. And so when we developed Webb, it was labeled as the Time Telescope, or a telescope that could see back in time to the early universe, 13 billion plus years. And so what we want to understand now, what I'm going to explain now with the remainder of my time, is how, again, we took these mechanical elements and blended them with some software elements in regards to what I can speak on to amplify these instruments and allow us to get these pictures, or images rather. And so here we have the team of, well, it's not a team, but a team of engineers from Ball Aerospace, which is now BAE, the SETI Institute, so the Space Telescope Science Institute, and NASA's Goddard Space Flight Center use data that we have in order to help align this telescope. And so align, or rather calibrate. And so on screen, you'll see there that we have the map of our 18 segments of the primary mirror. And each of these mirrors, when it started off, operated as individual sections. So you just had 18 telescopes up there, right? And so part of the process that we had was to break it down into 7 phases. These 7 phases took 3 months, or roughly 90 days to do. And over the course of those 3 months, we fully aligned the telescope in what's known as instrument commissioning. And so as you all know, you're all software engineers. Commands go up, telemetry comes down. We have a set of commands that are built into the data packages for our satellite based on the systems that are on there, and telemetry feeds back to let us know if it worked or not. And so when we look at this alignment, let's keep in mind that all the images I'm going to show you, except the next one, all the images I'm going to show you are not meant to be pretty. They're not meant to be the final product of what's happening. They're merely for the calibration process of our time here together. Because again, we want them to work as a single mirror and not 18 separate segments that are just arbitrarily separate. And so to put in perspective for you again, part of those 344 single points of failure is we also have to calibrate and get these things within what was our margin? Our margin was 50 nanometers in terms of how closely these things had to be aligned in order to actually achieve the results we wanted to achieve. So 50 nanometers was approximately what we had to work with. And so one of the questions is, how do we utilize onboard software, or rather, how do we utilize onboard software to help handle a small portion of the the software responsibilities on this massive program that we have? So early on in the program, as we know, the program didn't launch until the 2020s, but early on in the program, in 2007, it was announced that IBM would actually be in charge of one of the larger software packages for this program, and they'd be using the Rational Rows Real-Time, so RRT. And it was developed by IBM to handle a lot of so in space and command and telemetry databases and things of that nature, there's a lot of time-sensitive, time-critical events that need to happen, because not only this thing is orbiting, but you have to also collect the data from its down station as well. So everything is time-critical when it comes to these times. And so the application for James Webb was developed using the RRT platform using C++ language. I think it has a combination of Python somewhere in there as well. And so RRT, we know RRT to be a UML-based visual modeling software that helps just for you to drag and drop in some areas. It makes it slightly easier, or so I've heard, because I'm not on that team. I'm on the mechanical team. And so we've actually been looking at this picture a while, so let's switch there. So, ooh, okay. And so back to the software talk. So the software talk, actually, the software handles guidance, navigation, commanding, and instruments, and ISOM. So command, guidance, instruments, and the data downlinks. And so Goddard defined and then implemented using RRT a set of standard tasks that would allow it to control the command packets and receive telemetry packets. Again, commands go up, telemetry comes down. And so I had to switch the screen because we've been looking at that for a long time. But quickly, this image is actually known as Herbig-Haro 211. It's actually a star being born. It's a young star being born. And we almost think it's similar to our sun, something along the lines of our sun being born. And what happens with Herbig-Haro objects of form, these things coming out the ends are basically gas jets coming from the star heating up as it begins to be born. The colors are just, again, that infrared light moving through the universe, and these different wavelengths and variations come into NIRCam or what have you, and they're verified as to be along those wavelengths. So anyway, without further ado, so what is the process we follow to combine mechanical, software, and other skill sets to get to these amazing images? So first, again, remember, this is a 7-step process. So first, we had to do what's known as segment image identification, which is the need to align the telescope relative to the actual spacecraft. So if you count those little white blobs up there, you'll come up to 18 blobs. Each of those 18 blobs represents a segment of the James Webb Space Telescope and a segment of the primary mirrors. Some people have said they count 17, but there's a combination one. There's a larger blob down here near the bottom that actually counts as 2, just because of how the satellite was configured before it was launched. And so the spacecraft is capable of making these really extremely precise pointing moves, and we know that from using our star trackers on board. Again, the star trackers on the hot side, but the star trackers on board help us to aim at a star arbitrarily. Well, it's not arbitrary. We aim at one of the brightest stars we know, which is HD 8466, HD 8466, one of the brightest stars we know, and it's not near any other bright stars, so it's easy to focus on that one. So we focused our instrument known as NIRCam, which is on James Webb, at this relatively isolated bright star, again, HD 84406, to capture the series of images that would eventually be stitched together to form what we know today as the calibrated James Webb Space Telescope. So if you take a look at this here, this is going to be the image of each of the segments and what each segment returned back to us. So right now you see it's scattered, right? This looks nothing like the James Webb Space Telescope, much less it looks nothing like a singular picture. But all of these are looking at the exact same star, right? The exact same HD 84406 star, looking at the exact same thing. So what we had to do over the course of these 3 months was again, constantly feed our command packets this information and constantly and slowly receive the telemetry data back that this thing or this satellite was actually moving into place properly. And so one by one, we would move those mirror segments until they were all in the right area, and we can move on to what we know as, we called this image when it was complete being this image, the image array, just the array of the satellite up to this point. And so the next step we'll do is known as segment alignment. And you can see there should be an image playing there. So segment alignment is all we did was we then, the first step again was commands up, telemetry down. We shifted the position of each individual mirror one by one until it formed almost that shape that James Webb has. So you can see in the images, it comes into focus from being blurry. It starts to take almost the shape of James Webb now. And on this side here, the heat map of the telescope there shows you again how hot or cool the telescope was during this time. Because again, remember this on the cold side, but you can see some of the panels are actually warmer than the others based on how close it is to the hot side of the telescope. And again, that's because it's a 16-meter difference between the cold side and the hot side, and over 100 Cs different. And so after we have the image array, we can form what we know as segment alignment, which corrects most of the large positioning errors of the actual mirror segment. And so we do this through mathematical analysis known as phase retrieval. And so this phase retrieval for each of the mirror segments and the secondary mirror itself is all about the optical abrasions that we're trying to get out the way when it comes to making sure these things are in focus. So we begin to defocus the image or the segment images by moving the secondary mirror slightly to adjust for that accommodation that we see in those primary mirrors. So we got the segment identification to make your image array for just your dots of where everything is, and you take that and you do segment alignment so that it forms into what we know is the shape of the James Webb Space Telescope. Step 3 is known as image stacking. So then you're going to take each of those images and you're going to focus them into a single point. So if you look at James Webb again as an observatory, which it is, you want the light from the universe to come into the 18 panels, and you want it to then bounce back into that secondary mirror, and the secondary mirror reflects it back into the very middle of the telescope, which feeds into the instrumentations on the back, or the instrument module known as ISIM on the back. ISIM is comprised of 4 instrument suites from near infrared cameras to mid-infrared cameras to spectrometers to help us form spectrographs and things of that nature. So to put all the light in a single place, each segment, each image that we had from our image array and then from our segment alignment had to be stacked one on top of each other. And you can see in that visual there that each of them formed, or each of them stacked until it formed into the middle to follow that process that I just walked you through. So the third phase of this process, which again we know as image stacking, is we are now, again, tilting the mirrors inward, kind of at a diagonal angle until we get to that point. And through the stacking process, the mirror segments we've managed to get into this point are done in 3 groups, sections A, B, and C. It moves from the inside to the outside of the panel. So working our way from, I guess that'd be A1 and B1 all the way out to B3 at the ends. And so we broke this into 3 steps so that it was a little easier for us to do moving forward. And so moving on to the next step, after you have image stacking, we move on to what's known as coarse phasing. And so coarse phasing is basically how do I sum this up? Coarse phasing is when we utilize the detectors for coarse phasing, and based on these detectors that we have for coarse phasing, you can see in the image behind me there, it'll circle back around, but you'll see pistons moving up and down. And so this is part of that command package that allows us to actually move the back part of each of our mirrors, which are suspended onto pistons. And these pistons can tilt, these pistons can go up and down based on what we need to do. Again, we have that 50 nanometers margin of error in order for our telescope to work correctly or it go horrifically wrong. So although image stacking helps us to put each light image into one place of the detector, the segments are still acting as 18 smaller telescopes up until this point. And so the segments need to be aligned with an accuracy that, again, is smaller than a certain wavelength that we say at 50, but each one is broken down to less than 50. And so we did coarse phasing 3 times over the commissioning process, again, in those 3 phases, but then each of the 3 phases had multiple runs and attempts at it. So using a technology that we know as dispersed fringe sensing, we use NearCam to capture light spectra from 20 different pairings of those mirror segments. And then using those mirror segments, we then broke them into groups again and pointed them again toward where they needed to go. So we control the pistons of the segments so that they come together to form and create this monolithic primary mirror that we can then use as the primary means for the James Webb Space Telescope. So this is coarse phasing. Moving on to step 5 here. After you do your coarse phasing, after you get your pistons aligned, up and down motions, side to side motions for your pistons, we then move into what's known as fine phasing. We then turn to a different way of doing phase retrieval across the entire aperture of the telescope, all at the same time. So instead, we have some lenses that are in one of the scientific instruments and use it to automatically rate or defocus parts of that image in order to, again, recycle that motion of phase retrieval there. And so we can look at these images and taken as a whole, we can tell that there's only a little bit of alignment left when it comes to these images, because now it's not scattered, now it's in a center point, and now we're basically adjusting aperture, we're basically adjusting focal length and things of that nature in order to get it to an area where we actually collect data from it. And so fine phasing is also conducted, again, go figure, in 3 phases, right? So in 3 phases, so directly after each round of the coarse phasing, and then routinely throughout the entire lifespan of James Webb, you'll see that fine phasing comes into, again, because you have to continue to focus your camera or continue to focus your instruments to make sure that things are moving the way you want them to do. And by using this, we see that the secondary mirror also needed to be fine phased as well, not just the primary mirrors. And so again, through this specific data pack, what we found is that there was, once the entire mirror was focused on this one image that you can see through the fine phasing, the telemetry packets almost doubled in size, right? And that's because it was taking multiple images of the same location that we were just processing over and over. In those 3 cycles, the telemetry package increased, which allowed us to do additional downloads when it came over our drop zones for orbit, which are in different places around the world, not the US, around the world. Okay, and so there's only one thing left to do after you do your fine phasing. This telescope is well aligned at this point, using NearCam in the field of view for NearCam, which is, again, one of the primary instruments on the mission. And now we can extend the alignment to the rest of the instruments. And so the rest of the instruments that are in ISOM, those 4 instruments in ISOM, which again are on the code side, you've got your set of cameras and the spectrometers on the observing side. And so we do the instruments at the very end because there's no point in them looking at random spots in the universe. They need to just look at one intense spot, and so it comes after the phase focus area. So in this phase of the commissioning process, we make measurements at multiple locations or field points across the instruments, and it's shown in this image here. To not bore you with the details, we use an algorithm that calculates for final corrections, and then it moves into what we know as a singular point or a singular dot that you'll see up there. And so after applying the field of view corrections, the key thing left to address is the removal of small residual positioning errors, more or less. So just cleaning things up. And what you get here is, this is actually a selfie that was taken that was in the news for the primary selfie off the secondary mirror. And then this image over here is the final rendition of HD A4406. So that's the star that we started off with. That was 18 different points. We focused in on one point through those 7 phases. You saw it initially in visible light because it was darker, and now you're seeing it in more infrared light from now that near cam and the rest of the instrumentations are up and running appropriately. You can see it in the near field of view. The near infrared view. And so throughout this process, we've seen a number of gorgeous images from James Webb that are all available online for you to see. This, again, image of the Pillars of Creation. But it's important to understand that Webb's cameras are far more sensitive than anything we've sent up before, far more sensitive than a smart camera, far more sensitive than any of our Earth-based observatories as well. So instead, image specialists at the SETI Institute, which is in Baltimore, Maryland, are carefully helped to process each of these color images. And so, to put in perspective for you, the first pillar of creation was the Hubble image from 1995, was a stacked set of over 30 images from an astronomer, because they take so many images, they stack them on top of each other, and then they extrapolate the details as necessary, because some are out of focus, some are missing the point, because again, this thing is not millions, but several light years away. And so in addition to sending multiple images of the same target that need to be combined, Webb also observes infrared light, which is beyond what our eyes can perceive. And so through image stacking, you start with, again, more of the visible light spectrum. Most of the images that you see from Webb are actually black and white. They come in black and white, but what we get from the data from the spectrographs that we have is actually along the visible light spectrum, what wavelength that correlates with. And the specific wavelength of visible light, infrared light that it correlates with, allows us to know how old the object, the planet, the galaxy is that we're looking at. Because again, cosmological redshift, it's getting redder and redder, so we know that's older and older, right? And so through knowing this, we're able to help map out these colors even better. And so, and fun fact, you can actually utilize the James Webb Space Telescope data as you want to kind of play with in your own free time. That's on NASA and SETI's website as well. So let me land this plane here, because I heard I have Q&A as well. There it is. So comparing infrared and visible light, and so we know Hubble images of Uranus and Neptune, and so what does infrared light show us? Infrared light allows us to see the rings that are around this planet, because again, the light, the very minimal light that you find from a ring that's hundreds and thousands of millions of miles away or kilometers away isn't going to make it through the Earth's atmosphere or even through some of the advanced telescopes that we have in low Earth orbit. So the enhancements in infrared light allow us to actually see the rings a lot clearer around these planets. Even much more distant planets as well. And so next up in our exploration of the universe is known as the Nancy Grace Roman Space Telescope. This picture here is just showing you the field of view that we'll be able to see. Has anyone heard of the Roman Space Telescope? Okay, well, next greatest thing is going to be the Roman Space Telescope. To put again in perspective for you, that is the field of view for James Webb, and then the Nancy Grace Roman Telescope is obviously the larger one. So what it's going to allow us to do is see a lot larger swath of the universe all at one time, and then that'll allow us to point James Webb in these specific areas to collect that data from those areas. And so today, James Webb has helped us to discover an exoplanet, for example. I'm not saying what may or may not be on the exoplanet, because I can't, but it has discovered exoplanet today here, and we continue to hope that it discovers additional things that are just as exciting moving forward, and the Roman Space Telescope will do even better. I got one more project for you as well. I don't know if you all have heard of the Habitable Worlds Observatory. Show of hands. Okay, well, that's after the Nancy Roman Grace, and the project does exactly what the name implies, is a project intended to discover habitable worlds within the universe. I don't know when it's going to launch. We announced it last year sometime. But our hope is, again, that artist rendition on that side, that we discover something similar to Earth 2 orbiting a sun or a star system that is in the habitable or the Goldilocks zone, which is, again, the area around a star or a sun where water can exist, which allow life to exist. So the next latest and greatest program coming out is the Habitable Worlds Observatory. I'm really excited to get the opportunity to potentially work on that. And then lastly, before we get into Q&A, I love to take this opportunity to impart on all of my engineering colleagues the importance of giving back to the next generation in some way. Go out to a school, talk to them about the importance of engineering, what you do, how cool the role is, or volunteer in some capacity. I have a number of roles that I do there in America. I've got a fun picture there, me in the bunny suit visiting some students, just showing them what we do at NASA and what we do in the space industry as a whole. And so anytime I get in front of engineers, I love to impart that on them, just to say, if you are not participating in that capacity, I really do encourage you to do that for the next generation, just so they can see what great things we can accomplish together. Ooh. And here we are for the last image here. This is an image, one of my favorite images that came out of the James Webb Space Telescope. It's known as the Green Monster. It's a supernova. It's a supernova from debris of a destroyed star. It's got the name the Green Monster here from this little circular part here, where it's actually a dying star. The blast of waves created from the explosion are basically slamming materials around against each other. And from images that produced back from James Webb is in the KCA nebula, I believe. Through images that we got back from James Webb, we're able to know for a fact that it's dying stars and then how old these dying stars are. And we'll continue to, again, map out these different wavelengths and these different opportunities to continue to explore our universe and not only see how the universe is formed, but also how things in the universe are ceasing to exist as well. And so that's my time. I appreciate you all for being here today. Thank you for the opportunity to speak, and I hope you enjoy the rest of your conference. I think we're doing questions also. Thanks.
All right. Give it up for Kenneth. Another round of applause. This is amazing. I mean, was that like the world's most expensive selfie there?
Pretty much.
Yeah, right?
Over $13 billion, right?
All right. So we do have time for a couple of questions, so I'm just going to run right into them. The first one from Tudor, how does the telescope know to always keep the cool side away from the sun?
So we actually have a flight team that controls or flies the bird, for lack of a better term. We fly it out of Baltimore, Maryland. I sat on the team for a little bit of time, but it's really up to the control system to make sure this thing doesn't rotate and flip the wrong way. And we know that from sensors that it's not going to do that, or that we won't let it do that.
Gotcha. All right. From Peter, given the extreme conditions and the very high level of reliability needed, how did you test a complex system like this?
So quick answer is this project was in development for over 2 decades. So a lot of testing. As you know, you might not know, but it was initially planned to be launched somewhere in 2015 or so. And so it was delayed multiple times until it ultimately launched almost 7 years after that. And so complex systems, we broke it down into smaller bites, basically. So vibration testing, thermal testing, safe to mate testing, things like that. So we break it down in smaller bites.
And I'm just curious, like, what is the distribution, like half test, half code, or like how does that work, throughout the life cycle of that?
So across the lifestyle, I'd say that testing was prioritized, so much so that we built what's known as a Pathfinder model. So if you see any version of James Webb that's just hanging out somewhere in the world that's not in space, that's the Pathfinder one that we built, which is basically a dummy model we build before we launch into space.
All right. Next one. How can a software engineer get into aerospace aviation field. How much electrical and mechanical engineering is expected? What university degree is recommended?
So as a software engineer, you don't need to really have electrical and mechanical engineering in order to work in this field. A huge part, I argue, more than the mechanical side of this project is actually software based. I mean, it's the brains of the mission. If not, we're just launching a box in this space. So you learn different parts about different teams from being on those teams. For example, I'm mechanical, but I learned a lot about software from just interacting with them and how we need to build our systems. So I would say each skill set is required, and you don't need to necessarily cross blend in order to get a job there.
And is there any degree that you recommend that kind of gets you there?
Yeah, I mean, mechanical engineering is the best. I shouldn't say that here, but mechanical engineering is my degree. But my wife is a computer engineer. And so I would recommend computer engineering, software engineering, systems engineering, electrical engineering. Engineering in general is a great way to get your foot in the door there, or just some skill sets to be able to attribute to the mission.
All right. Next one up. Given the extreme conditions and a very high level of reliability needed, how did you test a complete? Okay, I think we got that one already. What happens if there are technical issue on the telescope?
What happens if there's technical issues on
Telescope.
orbit?
Yeah. So what happens if like something goes wrong, and probably nothing went wrong, right? Like it's just amazingly worked. You tested it all out.
If something goes wrong on James Webb, we're screwed. No. So James Webb, dissimilar to Hubble. With Hubble, we built Hubble with a servicing hatch. And as you may know, we've actually serviced Hubble a number of times. Because of how far James Webb is, we did not build a servicing hatch because no one's going to make a mission out there to L2 to actually repair it. So that's part of the reasons why we talk a lot of those 344 points of single point failure. And out of those 344, around 150, 148 are actually on the mirrors themselves. And each of these mirrors are a couple $1 million to produce. And so if something does go wrong, fingers crossed, knock on wood, hopefully nothing does. But we've built in some precautions to get over that, because the 344 was for commissioning and actual deployment of the satellite. So now that we've got through that, it's not nearly as daunting of a task. It's more satellite operations. So we're worried about things like micro tears and damage to mirrors, but it's a pretty solid telescope.
Nice. I mean, those kind of challenges is amazing.
Yeah.
All right, another question for Peter. Were there any special organizational or project management challenges you did not expect up front?
Yes and no. I knew that it would be a really tough mission to work on. I didn't know the level of, scrutiny we would face, specifically when it came to like Congress and things like that, of getting the mission or getting the satellite up there. So it was an eye-opening experience from the political side. Definitely, I didn't know how political this thing would be. But so that's the only unexpected thing, I think. Overall, I mean, it's not a typical mission, but when it comes to satellite integration and building satellites, it was one of the most fun missions I worked on. This is my fifth satellite I've helped to build, and so it's an awesome experience to have.
Yeah, nice. Well, another round of applause for Kenneth.